In this video, we'll be talking about inductors, and as you may know, inductors are also used to store electrical energy, and inductors store electrical energy in magnetic fields, such that when current is applied across an inductor, it generates a magnetic field across the inductor. Then when you remove the current, the magnetic field comes back and induces electric current in the inductor. And the equation that connects the voltage to the current components of the inductor is V is equals to L di dt, and where L is the inductance of this inductor. L is the inductance of the inductor. Now there are a lot of things this equation can show us about the inductor. The first thing we have to learn from this equation is that if you were to apply a constant current across an inductor, the IDT would be 0. So that means that with constant current, with a constant I, V would be 0. V would be 0. So when you apply constant current across an inductor, the voltage drop across it will be 0. It will act as a short circuit. So in a DC circuit, you can as well replace an inductor with a short circuit. The next thing you want to know about the inductor is that a change of current has to happen within a finite time frame. What I'm saying in essence is that you cannot change the current flowing through an inductor from 1 ampere to 2 ampere in 0 time instantaneously. To buttress my point, consider this simple circuit here. If you were to close the switch and charge up this inductor, then you immediately, instantly, you all of a sudden open this switch. What will happen is that electric current will flow across this space to prevent the current from changing instantaneously. This is what is called arcing, and it can cause a voltage surge, surges that damage equipment. That is that. What if we were given the voltage and asked to find the current? We can just make I the subject of the formula by saying that V dt is equals to L di. Then we can integrate both sides. If we do so, we would have it that I is equals to 1 over L integral V dt plus I naught, where I naught I t naught, where this is the initial condition, and this will be the value of the current flowing across an inductor. The next thing we should know how to do is how to calculate the power dissipated across an inductor, and we know that power is equals to IV, so we can say that power is equals to Li di dt, or we could say that power is equals to V 1 over L integral V dt plus I naught. Now, if we wanted to figure out how much energy is stored in an inductor, we can do that by writing this equation like this: P dt equals Li di, and integrating both sides, we would have it that W, that is energy, is equals to L I squared, and that is the amount of energy stored in the capacitor. So say you had 3 inductors connected in series with one another, and you wanted to find their equivalent inductance. That is what was the value of inductance that you connect across here that will give you equivalent effect of these three inductances together. But first things first, we know that current flows right through an inductor, so we know that equal currents would flow through each inductor here. Then there will be a voltage drop across each inductor, so let's call the voltage drop across this one V1, and that across this V2, and that across this V3. So that would mean that V is equals to V1 plus V2 plus V3. This would mean that L equivalent di dt, which is the value of V, would be equals to L1 di1. So the next thing you want to do is you divide through by di dt, and with that way that the equivalent inductance is equals to L1 plus L2 plus L3. So if you connect your inductors in series in which one another, is expect the equivalent inductance to be the sum of all the inductances. What happens when we connect our inductors in parallel? Well, we know for sure that the same voltage flows across them, and then different currents flows through different inductors. So let's call this one I1. The current through this one would be I2, and the current through this one would be I3. So the total current, let's call that one I. So we know that I is equals to I1 plus I2 plus I3, right? Then refer back to this formula here. Let's say I is equals to 1 over L integral V dt plus I naught. So we can say that I is equals to 1 over L integral V dt plus I naught equals 1 over L1 integral V dt plus I1 naught plus 1 over L2 integral V dt plus I2 naught plus 1 over L3 integral V dt plus I3 naught. Now I1 naught, I2 naught, I3 naught, I naught, they are all equals to 0 under initial conditions. So this kind of disappear. Then we can divide through by V integral V dt. Then we'll be left with I L equals I1 over L1 plus 1 over L2 plus over L3, and then we know that this is what the equivalent inductance. This is the relationship between the equivalent inductance and the inductance connected in parallel. And that will be all for today. Don't forget to hit the like button and subscribe. See you next time. Bye.